So good day everyone. Today I will discuss the chapter 5, topic 4, reliability. For the topic outline, we have here the Spearman-Brown formula, other methods of estimating internal consistency, the Coder-Richardson formulas, coefficient alpha, average proportional distance or APD, measures of interscorer reliability, and the importance of the methods used for estimating reliability. The Spearman-Brown formula allows a test developer or user to estimate internal consistency reliability from a correlation of two halves of a test. It is a specific application of a more general formula to estimate the reliability of a test that is lengthened or shortened by any number of items. So the formula is stated here. So where RKK, reliability of a test, K times as long as the original test, R11, reliability of the original test, K, factor by which the length of the test is changed. To find K, divide the number of items on the original test by the number of items on the new test. If you had 10 items on the original and 20 on the new, K would be 20 divided by 10 is equals to 2. So the Spearman-Brown formula is also called as the Spearman-Brown prophecy formula. It is a measure of test reliability. It's usually used when the length of a test is changed and you want to see if the reliability has increased. So example question. A test made up of 12 items has a reliability or R11 of 0.68. If the number of items is doubled to 24, will the reliability of the test improve? So for the solution, you just have to insert the given numbers into the formula and solve. We are given, so the R11 is equals to 0.28, K is equal to 24 divided by 12 is equals to 2. So RKK is equal to 2 multiplied by 0.68 divided by the sum of 1 plus 2 minus 1 multiplied to 0.68. So the result is 0.81. So doubling the test increases the reliability from 0.68 to 0.81. For the formula to work properly, the two tests must be equivalent in difficulty. If you double a test and add only easy 4 questions, the results from the Spearman-Brown formula will be invalid. Although increasing test items is one way to increase reliability, it's not always possible to do so. For example, doubling the already lengthy GRE would lead to examinee fatigue. So based on the Spearman-Brown formula, we can see that increasing the number of items on a test by any number will increase the predicted reliability of a test. So if test developers or users wish to shorten a test, the Spearman-Brown formula may be used to estimate the effect of the shortening on the test's reliability. Reduction in test size for the purpose of reducing test administration time is a common practice in certain situations. A Spearman-Brown formula could also be used to determine the number of items needed to attain a desired level of reliability. In adding items to increase test reliability to a desired level, the rule is that the new items must be equivalent in content and difficulty so that the longer test still measures what the original test measured. So, using this logic, we might think that increasing the length of a test by a massive amount of items is a good idea because we could push the reliability closer and closer. However, closer and closer to 1. So, however, we should keep in mind that using too many items can cause fatigue effects. If a test has too many questions, then individuals may become fatigued as they answer more and more questions, causing them to produce less reliable answers as the test drags on. And also, the new items added to the test should be of equal difficulty to the existing items. It is important that if we do decide to increase the length of a test, that we make sure the new items or questions we're adding are of equal difficulty to existing items, otherwise predicted reliability will not be accurate. So, other methods of estimating internal consistency. So, inter-item consistency refers to the degree of correlation among all items on a scale. An index of inter-item consistency in turn is useful in assessing the homogeneity of the test. Tests are said to be homogeneous if they contain items that measure a single trait. Heterogeneity describes the degree to which a test measures different factors. So, internal consistency reliability is a way to gauge how well a test or survey is actually measuring what you want to measure. A simple example is you want to find out how satisfied your customers are with the level of customer service they receive at your call center. So you send out a survey with 3 questions designed to measure overall satisfaction. So choices for each questions are strongly agree, neutral, disagree, and strongly disagree. So I was satisfied with these are the questions. I was satisfied with my experience. I will probably recommend your company to others. If I write an online interview, it would be posted. It would be positive. If the survey has good internal consistency, respondents should answer the same for each questions. Example, 3 agrees or 3 strongly disagrees. If different answers are given, this is the sign that your questions are poorly worded and are not reliably measuring customer satisfaction. So most researchers prefer to include at least 2 questions that measure the same thing. The above has 3, so you can use 2 or 3 questions that measures the same thing. So let's proceed to the Kuder-Richardson formulas. Kuder-Richardson formula 20 or KR20, so named because it was the 20th formula developed in a series. KR20 is the statistic of choice for determining the inter-item consistency of dichotomous items, primarily those items that can be scored right or wrong, such as multiple choice items. So, the Kuder-Richardson formula 20 is often abbreviated as KR20. It is used to measure the internal consistency reliability of a test in which each question only has 2 answers, right or wrong. So how is KR20 computed? The following formula may be used. So this is the formula. So where RKR20 stands for the Kuder-Richardson formula 20 reliability coefficient. K is the number of test items. Variance is the variance of the total scores, P is the proportion of test takers who pass the items, and Q is the proportion of people who fail the item, and the last one is it is the sum of the PQ products all over item. So the value of for KR20 ranges from 0 to 1 with higher values indicating higher reliability. So for example, suppose we administer a test with 7 questions to 10 students. The result of the test are listed below in Excel with 1 indicating a correct answer and 0 indicating an incorrect answer. So as this can quickly get used for tests with large number of items, it's usually calculated with some type of software like Excel. So since this value is extremely low, this indicates that the test has low reliability. This means that questions may need to be rewritten or rephrased in such a way that the reliability of the test can be increased. So if the result is low, so the questions maybe need to be rewritten or so here is the table with the data wherein 0 is the Q and P are the 1. So you can see here that the K is 7, 7 and the EPQ is the 1.57 and the variance is 1.6556. KR20 is equal to 0.063. So the KR20 value turns out to be 0.0603. Since this value is extremely low, this indicates that the test has low reliability. So this means the questions maybe need to be rewritten or rephrased as what I've said earlier. So numerous modifications of Kuder-Richardson formulas have been proposed through the years. The one variant of the KR20 formula that has received the most acceptance and is in widest use today is statistic called coefficient alpha. What is this coefficient alpha? It is developed by Cronbach in 1951, and coefficient alpha may be thought of as the mean of all possible split-half correlations, appropriate for use on tests containing non-dichotomous items. The formula for coefficient alpha is below. So this is the formula of coefficient alpha, where N is equal to the number of items, C is the average inter-item covariance among the items, and V equals the average variance. So one can see from this formula that if you increase the number of items, you increase Cronbach's alpha. Additionally, if the average inter-item correlation is low, alpha will be low. As the average inter-item correlation increases, Cronbach's alpha increases as well, holding the number of items constant. So a rule of thumb for results. So a rule of thumb for interpreting alpha for dichotomous questions, example questions with two possible answers or Likert scale question is this Cronbach's alpha. So internal consistency, if it is above 0.9, it is considered as excellent. If it is 0.8 to 0.9 good, 0.7 to 0.8 acceptable, 0.6 to 0.7 questionable, 0.5 to 0.6 poor, and below 0.5 is unacceptable. So in general, a score of more than 0.7 is usually okay. However, some authors suggest higher values of 0.90 to 0.95. So Cronbach's alpha tests to see if multiple question Likert scale surveys are reliable. These questions measure latent variables, hidden or unobservable variables like a person's conscientiousness, neurosis, or openness. So these are very difficult to measure in real life. So Cronbach's alpha will tell you how closely related a set of test items are as a group. Let's proceed to the average proportional distance, or the APD. So APD is a measure that focuses on the degree of difference that exists between item scores. Accordingly, we define the average proportional distance method as a measure used to evaluate the internal consistency of a test that focuses on the degree of difference that exists between item scores. So APD would be calculated as follows. So step 1, calculate the absolute difference between scores for all of the items. Step 2, average the difference between scores. And step 3, obtain the APD by dividing the average difference between scores by the number of response options on the test, minus 1. So for the 3ITE, here is how the calculations would look using Yolanda's test score. Step 1, absolute difference between items 1 and 2 is equal to 1. Absolute difference between items 1 and 3 is equal to 2. And absolute difference between items 2 and 3 is equal to 1. So in order to obtain the average difference, or the AD, add up the absolute differences in step 1 and divide by the number of items as follows. So AD is equal to 1 plus 2 plus 1 divided by 3. So 4 over 3 is equal to 1.33. Then step 3, to obtain the average proportional distance, or APD, divide the average difference by 6. The 7 response options in our ITE scale minus 1. So there is 7 response options. So minus 1 is equal to 6. So using Yolanda's data, we would divide 1.33 by 6 to get 0.22. So the general rule of thumb for interpreting an APD is that an obtained value of 0.2 or lower is indicative of excellent internal consistency, and that a value of 0.25 to 0.2 is in the acceptable range. A calculated APD of 0.25 is suggested of problems with the internal consistency of the test. So accordingly, we define the average proportional distance method as a measure used to evaluate the internal consistency of a test that focuses on the degree of difference that exists between item scores. So as time passes, people change. For example, people may learn new things, forget some things, and acquire new skills. It is generally the case, although there are exceptions, that as the time interval between administrations of the same test increases, the correlation between the scores obtained on each testing decreases. So the passage of time can be a source of error variance. The longer the time that passes, the greater the likelihood that reliability coefficient will be lower. So when the interval between testing is greater than 6 months, the estimate of retest reliability is often referred to as the coefficient of stability. Proceed to the measures of interscorer reliability. Interscorer reliability is the degree of agreement or consistency between two or more scorers or judges or raters with regard to a particular measure. So interscorer reliability is often used when coding nonverbal behavior. So the simplest way of determining the degree of consistency among scorers in the scoring of a test is to calculate a coefficient of correlation, also referred to as coefficient of interscorer reliability. So it can also be called as inter-rater reliability. So inter-rater reliability or interscorer reliability is the level of agreement between raters or judges. So if everyone agrees IRR is 1 or 100%, and if everyone disagrees, IRR is 0 or 0%. So several methods exist for calculating IRR, from the simple example percent agreement to the more complex one. So which one you choose largely depends on the type of data you have and how many raters are in your model. So for the inter-rater reliability method, so this one is the percent agreement for two raters. So the basic measure for inter-rater reliability is a percent agreement between raters. So we have 5 contestants and we have 2 raters, judge 1 and judge 2. So, and these are the agreements. So in this competition, judges agreed on 3 out of 5 score. Percent agreement is 3 over 5. So the number 1 represents the agree and the 0 represents the disagree. So we have here 3 over 5, and if you convert that to percentage, it would be 60%. So to find percent agreement for two raters, a table like the one above is helpful. So first, the step is count the number of ratings in agreement. In the table above, that's 3. So next, count the total number of ratings. For this example, that's 5. Divide the total by the number in agreement to get a fraction. So 3 over 5. So convert to a percentage. 3 over 5 is equal to 60%. So the field you are working in will determine the acceptable agreement level. In general, above 75% is considered acceptable for most fields. So the field you are working in will determine the acceptable agreement level. If it's a sports competition, you might accept a 60% rater agreement to decide a winner. However, if you're looking at the data from cancer specialists deciding on a course of a treatment, you'll want a much higher agreement, like above 90%. So in general, above 75% is considered acceptable for most fields. So here is the percent agreement for multiple raters. So the previous one is the agreement between just two raters, and here is the agreement for multiple raters. So make a table. So step 1, make a table of your ratings. For this example, there are 3 judges. So we have 5 contestants, and we have judge 1, judge 2, and judge 3. So step 2, add additional columns for the combinations pairs of judges. For this example, the 3 possible pairs are judge 1 and judge 2, judge 1 and judge 3, and judge 2 and judge 3. So step 3, for each pair, put a number 1 for agreement and 0 for disagreement. So for example, contestant 4, judge 1 and judge 2 disagreed, so it would be 0. Judge 1 and judge 3 disagreed, so it is also 0. And judge 2 and judge 3 agreed, so it is 1. So and so on, it follows. So step 4, add up the ones and zeros in an arrangement column. So for the contestant 1, we have 3/3 agreement, and for the contestant number 2 we have 0/3 agreement. So for the contestant number 3 we have 3/3 agreement, and for the contestant number 4 we have 1/3 agreement, and for the contestant number 5 we have 1/3 agreement. Step 5, find the mean for the fractions in the agreement column. So mean is equal to 3/3 plus 0/3 plus 3/3 plus 1/3 plus 1/3 divided by the number of agreements. So we have here 5 number of agreements, so it is equal to 0.53 or 53%. So the iterator reliability for this example is 50%. So the last one is the importance of the method used for estimating reliability. So as noted throughout this text, reliability is extremely important in its own right and is also a necessary but not sufficient condition for validity. However, researchers often fail to understand that the specific method used to obtain reliability estimates can lead to large differences in those estimates, even when other factors such as subject, sample, raters, and specific reliability statistics used are held constant. Are the references, and that would be all. Thank you.